And with this, we complete 1 year of Curie Club also. In the last 1 year, we had lot of activities like faculty, guest and we had one Chem week also, which we will be having in this November again. And we had other activities like chemistry demonstrations, poster competition, etc. So in this series today we have with us Professor K.S Viswanathan, Head Department of Chemical Sciences and Faculty Coordinator Curie Club. So to give a talk on chemistry in cages. So to introduce Professor Viswanathan, he is born on September 5. Yes, September 5. And then he did his PhD from 1979 to 1983 in Vanderbilt University. From 83 to 85, he did his postdoc in Indiana University. And then from 86 to 2011, he worked in analytical and spectroscopy section of materials chemistry division in IGCAR Kalpakam. And then he took over as professor chemistry in IACR Mohali. And now he is the head and faculty coordinator Curie Club. So let's all welcome Professor Viswanathan.
Thank you. I think you said you finished 1 year of Curie Club. I think you finished 2 years of Curie.
2 years.
Yeah. I know you started at
Officially 1 year. One unofficial.
So this counting of the get done. Yeah, thanks. So what I will, the Curie Club, I think it's a nice group that they've got together, and I will urge all of you to actively participate in that. I think you must go beyond lecture. I mean, at 9 o'clock, somebody come and talk to you. It'll be boring. Let's have some other activities that makes it more interesting, and like he was talking about quizzes and demos. I think you need to come up with many variations and keep the club as active as possible, because it's a good way to.
I'm sorry to interrupt you. Can you use a caller mic, sir? People can't hear you.
Sure. Okay? Picking up. So I think you need to have activities and keep this club as active as possible. That's the whole idea of the Curie Club. Particularly those who have joined us this year. I think this is there are many clubs, and there is one such, and it's able to be actively participating in these just to enhance your knowledge. Classroom is not the only place where you learn, and you probably learn much more outside when you classroom. Okay, what I'm going to do today is talk to you about chemistry in cages. Most of these stuff drawn from work that we have done over the years. And just to highlight to you how the environment of the molecule can completely alter the course of the reaction. It can give rise to new reactions that you haven't thought of. When I say environment, I'm talking about confining the molecules to certain region in space. And if you can do that, the molecules will react differently quite often. You can also stabilize structures that would otherwise not have been stabilized if you let the molecules wander around. So what we will do is essentially look at how cages can influence reaction properties and structural properties of molecules. And that is what we will talk about today. And the last few slides I'm going to draw from stuff in the literature, just to tell you how well these reactions can be done and how well chemistry can be made more interesting just by running these reactions under conditions where the molecules are confined in a certain region in space. You can do that. Not surprising, because the free line and the cage line, very different property. You wouldn't want to be close to this, but you have no problem being close to this. So that's straight away a situation where you know that just by caging something, the properties are going to be essentially different. Chemistry is no different. That's probably very convincing as to why this title is being chosen. And almost everything that I'm going to be talking, almost 90% of what I'm going to be talking today will stem from spectroscopic study. That's the only thing we know. Therefore, we see how we can use spectroscopy studies to essentially look at K effects in molecules. Well, just to give you a little rundown, spectroscopy essentially is so you can have basic studies in spectroscopy. By basic studies, I mean you can look at molecular structure, you can look at weak intermolecular interactions. Essentially, you can get properties of molecules by doing spectroscopy. What you can also do is use spectroscopy for applied situations where you understand engineering processes and technological processes. You can develop new analytical methods and facilities for process monitoring, and that's where spectroscopy again comes in extremely handy. So you can use it on the one hand to look at fundamental properties of molecules. You can turn the problem around, and based on what you have learned from these fundamental properties, you can turn it around to study concentration, function of time that you would need in a process, in a big engineering technological process, and that's basically what you would do. So you have both basic as well as applied situations that one can look at when you're doing spectroscopy. Of course, spectroscopy has many manifestations, and you've seen that. Some of you will be seeing that in the near future. We have microwave, infrared, fluorescence, NMR, GSR, and what have you. And you're all looking at the way the molecules behave, shine light at different frequencies. They all do different things depending on what frequency you shine on them. Your fluorescence spectroscopy can use a laser and cause a breakdown in the molecule when it's completely ionized, and using that you can essentially get to know about the molecular structure, properties, and concentration, and what have you. What we will be looking at today is mostly the spectroscopy in cryogenic mediums, meaning that we're going to be looking at molecules that are trapped under conditions of 10 Kelvin. And the reason why we're going to be doing that is essentially to put molecules in a cage. Because the 10 Kelvin molecules can't move. So essentially you have confined the molecules into a region in space, and now you're going to be hitting them with photons or hitting them with whatever else that you can in terms of providing energy to the molecules to dissociate, and then see what happens. What we are trying to do is to have these molecules confined in regions of space. Confinement is caused both by the fact that there are molecules around which are preventing them from moving away, and confinement is also caused by the fact that you have molecules that can help them. They don't have much energy. We've been harping on this KT all along. KT and 10 Kelvin is hardly anything. The molecules really don't have much energy to keep moving. They're very sluggish, and that sort of confines them to region in space. And then you can look at chemistry under these conditions. You'll find the chemistry at that temperature. Sometimes it can be very different from the chemistry that you see at 300 Kelvin, which is a room temperature. So that's basically what we're going to be looking at. I can produce cages, a solid state cage in which I have crystals or low temperature inert gas solids. When I say low temperature inert gas solids, I'm talking about 10 Kelvin. So that 10 Kelvin or thereabout, because you can go down to even 4 Kelvin and lower. Almost everything excepting hydrogen and helium are solids. Everything. So you have carbon, nitrogen, xenon, krypton. All these inert gases are solids. Therefore, if you freeze them out at 10 Kelvin, you essentially have a solid state material, which is a solid state crystal of the inert gas. If you dope your molecule or flip this, now this molecule is essentially confined in this cage. And then you can look at the chemistry of these molecules under these conditions. You can also have cages in solution phase. How can I do that? If I take a very viscous solution, a viscous solution will prevent molecules from diffusing away. Therefore, I don't have to go to 10 Kelvin. I can still have molecules at room temperature, but by simply having a solution which is extremely viscous, I can cause confinement and therefore lead to chemistry under confined conditions. And we will look at some examples of interest where you have interesting structures and you have reactions that are influenced by these games.
So,
Yeah.
so solid state phase, why the molecule of our interest is the particularly inert gas? Why don't we choose the other? That means only inert gas. Why we are choosing only the inert gas? Why not the other?
Yeah, we could choose anything, but I will tell you why we're choosing inert gases as we go along. But you're right, I don't have to choose inert gas. I can probably do a reaction with hydrocarbons, which are not as inert as argon, nitrogen, and krypton.
So that
Yeah, I could do that. Or I could do it in solid carbon dioxide, or I could do it in maybe solid benzene. You could. But as we go along, we will see why we're choosing the inert gases and not something that is very reactive. How do you prepare cages? This is something that you do. Question that we raised, I can have inert gas cages at cryogenic temperatures. I need cryogenic temperatures because it's only at these temperatures I can have inert gases solidified. I can't have inert gas cages at room temperature. They are gas. I can make solid state materials, crystals, in which I can dope the material and then conduct these confined reactions at room temperature. Or I can use molecular templates. We will see what that means as we get along. You can have molecular templates in which this molecule is actually located, and this molecular template will actually provide the confinement that we are talking about. Now, actually doing experiments with inert gas cases, what I'm essentially trying to do is I'm trying to isolate the molecule of interest in the solid inert gas lattice. That's the reason why we call it as matrix isolation, because I'm isolating the molecule in a solid inert gas matrix. How do I do this? I simply, a lot of space out here. So how do I do the experiment with the inert gas? How do I take the molecule and start it in the inert gas solid? It's following method. Never seen a glass before. Stay out here. You just come over here. Run outside. Pradeep, run outside. Put a little board. Housefull. Okay. So how do I do this experiment where I trap this, where I put this molecule in a solid inert gas cage? First, I need low-gas filters, and I also need this molecule to be isolated in this cage. So if I'm looking at preparing these cages, what I need to do is I have to mix a sample or mix the molecules that I'm interested in. Molecules on which I want to do the reaction. I mix those molecules with a very large excess of an inert gas. When I say large excess, I'm talking of one molecule of interest to 1000 atoms of carbon. That's the ratio I'm talking about. So when you do that, let's say I'm looking at acetylene. I want to look at the spectroscopy or reactions of acetylene. So I take acetylene and argon, and I take one molecule of acetylene for every 1000 atoms of argon. So that's the ratio in which I prepare a gas mixture. Acetylene is a gas, argon is a gas. So all I have to do is take 1 core of acetylene and 1000 core of argon and mix them using manometric procedures. Then essentially I have 1 molecule of acetylene and 1000 atoms of argon. I need this large excess, and you will see very quickly why. And then I have the gas mixture prepared here. I fuse the gas mixture into vacuum. And here is a little plate. It could be a potassium bromide plate if I'm doing current spectroscopy, it could be glass plate if I'm doing optical spectroscopy. There is some substrate on which I'm going to prepare my sample. I'm going to deposit my sample. And this is going to be held at 10 Kelvin. And how do I get 10 Kelvin? It's using a refrigerator, which is very similar to what you have at home, excepting that the home refrigerator does not use helium. This refrigerator uses helium as the working gas. Let's not get into how that works. It simply compresses and expands helium, and in that process gives a low temperature. And I get 10 Kelvin back. So I have 10 Kelvin out here, and as the gas mixture refuses, it will all go and sort of solidify on that, because at 10 Kelvin, as I said, everything other than identity is solidified. So argon will solidify, and acetylene also will solidify on that little plate. But since I have smartly chosen the ratio to be 1000:1, what do you expect to happen? You expect to see argon everywhere, and these little acetylene molecules sitting here, there, and somewhere, and it's highly improbable that 2 acetylene molecules are going to be close to each other. Statistically improbable, because I have chosen such a dilute situation. And why do I choose inert gas? Question he asked me, I choose inert gas because I want acetylene not to interact with this gas. If I had chosen something else like HCl, then my matrix. If I had trapped acetylene and HCl, then acetylene is all the time reacting with HCl. Because acetylene has got basic sites, HCl is acidic, and therefore perturbing acetylene all the time. I want to conduct a reaction of acetylene where acetylene is not perturbed by other molecules. All these inert gas molecules are going to be doing is providing the cage. After having provided the cage, they do nothing more. Just like the lion in the cage, all the cage does is to keep the lion inside. If this cage was, having electric current passing through it or things like that, which is going to kill the lion in the eventual process, we don't want that to happen. The cage just confines it and does nothing more. So the R1 is essentially something like that. It provides the environment to confine the molecules, but doesn't do anything more than that in terms of reacting with it. Why cryogenic matrix? Because I need to solidify R1. What happens when you have cold molecules? There are many advantages. First, of course, I needed the cold situation to trap the argon in there. But then I get a lot of advantages from that. One advantage is the fact that if I have extremely cold temperatures, then all these molecules will essentially get down to the low state. Whereas at room temperature, they might be populating many states. And if they're populating many states, without getting into the complications, they could be this transition, they could be this transition, this transition, this transition. You've got a whole mess of transitions out there. We call that as spectral congestion. And that's sometimes extremely hard to analyze that spectrum when you have a bunch of spectral lines that are really showing off in the spectrum. But if you quietly get all these guys down to the lowest temperature, lowest state possible, which is what will happen if you get down to 10 Kelvin, because at 10 Kelvin all the molecules sort of pull down to the lowest possible state, then the only transition you're going to have is maybe this and this. This transition that you had earlier is gone, this transition is gone. You've essentially killed off many transitions, so your spectrum becomes that much simpler. So that's one big advantage. So if you then go back to probe the confined molecule and look at all its funny reactions, it's easier for you to do that because this molecule is going to put off only one or two signatures and not a whole bunch of signatures, which is going to be extremely hard for you to analyze. So that's one of the reasons why this technique is nice. The 10 Kelvin was required to solidify your R1, but it gives you many advantages as a result. And that is, the spectrum is extremely simple. And therefore, you can go back and look at these molecules and be able to analyze them far more efficiently and far more simply than otherwise. We won't get into these things, the lines are broadened due to various reasons, but at lower the temperature, the spectrum looks sharper. Some of you already know this, some of you who don't know this will know this very soon. But the point is, this advantage you get, plus you get the advantage that many of the lines, which are usually broad at room temperatures, tend to get very sharp. And sharper the lines are, the better it is or easier it is for you to be able to analyze them. So, isolation does many things. Once you isolate the molecule, you reduce the intermolecular interaction. Right? Acetylene is a gas phase, where every acetylene is colliding with another acetylene molecule. That's acetylene talking to acetylene, and you don't want that. Whereas in the experiment that we have just done, in which we have trapped acetylene and argon, acetylene is at best trying to talk to argon, but argon won't talk to acetylene because it's in it. So acetylene is basically sitting there with no need to talk to. Therefore, you have basically reduced any intermolecular interaction, which is good. And that again, is another reason why the lines get sharp. There are any weak complexes that we will see. These weak complexes will survive at 10 minutes. Hydrogen bond energies are like 5 kcal per mole. The Kd is like 0.6 kcal per mole, which essentially means that some of the hydrogen bonds will get destroyed at room temperature. Because there are some molecules that are going to be much larger than the average, and those will keep destroying the hydrogen bonds. But if I take Kd and make it, instead of 0.6 kcal, if I make it 0.06 kcal, then the fraction of molecules having 5 kcal per mole is hardly any, and therefore these weak interactions will survive. And therefore, if I'm going to look at very weak interactions and look at unusual structures that are produced by these weak interactions, I have a much better chance of seeing them at 10 Kelvin rather than at 300 Kelvin. Yeah.
So when you say weak interactions and you are using acidity and suppose all the molecules, so having a first state, molecule state, so the weak interactions should also be very less as compared to it was initially, but it was getting disturbed initially. But now, how we are able to tap it?
Yeah. So this question is, I'm saying two contradictory things. Of course, I said they must isolate them. There are no interactions and so on. And now suddenly I'm talking to you about weak interactions. These two molecules will get together. What you essentially, you will see how it is done, but that's possible. Essentially what I do is I first keep these molecules all far away from each other, and they don't talk to each other. Then I slowly warm this. I was going to say this later, but since he's asked the question, I will say it right away. You just warm this substance from 10K to about 30K. I can't go above 30K. Because if I go to 35, 40K, argon will evaporate and go away, and there is no experiment after that, you go home. So what you have to do is to keep it at about 30K and leave it there for 30 minutes, half an hour, 1 hour, 1 hour, 2 hours, whatever it takes. So at 30K, you have just increased the KT a little, so as it tends to crawl here, there, and somewhere. And after a while, it will meet its rightful partner, and you would have formed this weak interaction. So the weak interaction is actually produced by this process of warming the matrix, providing some energy, making the acetylene molecules move, and find the rightful partner. Extremely slow process, but if you wait long enough, sometimes we have done this waiting for 2 hours, 4 hours, just to get these molecules to get together and form these complexes, and it can be done.
Sir,
Yeah.
does the crawling involve a cage breaking, or if the cage itself moves it?
The cage itself becomes loose at 30 Kelvin. The cage itself, the lower the temperature, because what I'm essentially doing is by heating it, I'm getting close to the melting point. And as I keep getting closer and closer to the melting point, the cage just tends to become a little loose, and that in a way enhances the diffusion of these molecules that I'm interested in to a small extent. All these are extremely small processes. That's the reason why you have to wait for a minimum of 30 minutes to a maximum of your lifetime to be able to get something out of that. So, yes.
You're also, so it's telling you're also decreasing the number of molecules that are going to analyze the spectrometer. Somehow, if it is not, you're not compromising with the intensities of the spectrum.
Oh. Next one. These things, you're taking so few molecules, can you even see them? You know, I harped on some, I didn't harp on it, I just sort of rushed through, saying that the peaks become sharper. Okay. At the end of the day, the total intensity that you get is the area under the peak. By sharpening it, what am I doing? A peak that was looking like this, the moment I sharpen it, it becomes pretty large. So essentially by sharpening it, I have improved my signal to noise, and therefore the process of sharpening essentially makes it easier for me to even look at very small intensities. The area will still be small, but the height will be large because the width is small. And that's how the peak sharpening is actually is very paramount importance for me in doing this. The peak had not sharpened, it was still broad, then forget this experiment would not have worked. Because if it is broad, and the area is extremely small, then the height or the intensity about the baseline will be so small that you probably won't even be able to see it with noise, but it would have worked. But the fact that the lines have sharpened is what saves the day for me.
So, sir, I'm diverting from the topic of spectroscopy, as the question was asked on the basis of the interaction. If the molecule has interaction at the room temperature, as compared to low temperature, it has more interaction. So, is it the case that if the molecule has intramolecule has more interactions at room temperature, more interaction at room temperature as compared to the lower temperature, so more interaction will give us more information. So then why we are going for low temperature, and why we are interested in knowing the weak interactions? At room temperature, we are getting stronger interactions, so we could get
No, the interaction does not get stronger or weaker. The interaction, let us say, is 0.5 kHz or 0.3 kHz or whatever. The average energy of the molecule, you have to look at the energy of the interaction versus the average energy. If the interaction energy is let's say 5 kHz, and your average energy is like, let's say, 1 kHz, and it is quite likely that the molecule has enough energy to keep breaking this 5 kHz per mole bond. By going to a lower temperature, I am not changing this 5 kHz per mole. All I am changing is reducing KT. So the average energy is now so small that this interaction will survive. That's all I am trying to do. I am not changing the interaction energy. I am just making the molecules lazy. See, for example, if I had something very loosely tied to my hand, wiggling my hand very hard, this is going to just break off. By going to a lower and lower temperature, what am I doing? I am reducing rotation energy, reducing vibration energy. And therefore, if the molecule is doing this, it does this. And therefore, whatever is held on doesn't break away. The strength of that is still the same. All I have done is make the molecules big and slower, either in rotation or vibration or what have you. So that's basically the whole point. Okay. Let me go on. So hence, therefore, you will see that the process of doing this cage study, it's important that I trap molecules at low temperatures and inert gas matrices. Why inert gas matrices? Because I want the molecules not to talk to the other people. I want the property of the molecule to be intact so that I can go and study. By going to 10K, 10 Kelvin, I have a solid cage produced. Therefore, I can look at these molecules trapped in the solid. So I'm making it look like I'm the process studying cage effects. Actually, when we did all these experiments, we were not looking at cage effects. Cage effects simply came on to us, and changed so many things that we got interested in it. But by trapping it at low temperatures, inert gas cage, the cage is formed, low temperatures, weak interactions can be stabilized and studied, and the molecule is also sitting in an environment in which the neighbors don't talk to it, therefore the property of the molecule is kept intact. And that's why this experiment works. This is just to give you a little cartoon as to how this experiment really works. If I take acetylene as a gas phase, this is what they do. They keep tumbling, they keep turning around, they keep interacting with each other. Therefore, every acetylene is looking at every other acetylene at any given point in time. However, if I do the experiment the way I just said, where you trap the acetylene in R1, and if you assume these policemen are all these R1, why are there so many policemen? Because there were 1,000 atoms of R1 to begin with in that ratio. Acetylene were far and few. And therefore,